Hi, my name is Hazim and today I will be talking about order of differential equations, its background history and a few examples with solutions. So, what's an ODE? An ODE is a differential equation that describes the relationship between several variables and the rate of change or differential in one variable. Now, let's talk about the history of ODE. So, what's the history of ODE? The history of ODE. Since its introduction in the middle of 17th century, differential equations have been a significant area of pure and practical mathematics. Leibniz, the Bernoulli brothers, and others first developed differential equations in 1680s, not long after Newton developed fluxual equations in the 1670s. Applications mainly to geometry and mechanics were made. Isoperimetrical issues were optimization exercises. So, now what's the ODE theory? The ODE theory states that the highest order derivative that a differential equation has is used to define the equation's order. The highest order derivative of a differential equation is defined as its degree, which is expressed as a power. If the function and all of its derivatives occur to the first power and the coefficient of each derivative in the equation solely concerns the independent variable x, the equation is said to be linear. Various forms of ODE exist, such as linear, nonlinear, homogeneous, and non-homogeneous. So now let's move on to the next slide where we'll be talking about applications of ODE in biotechnology. So there are four applications of ODE in biotechnology. There are many biological laws and relationships which can be expressed mathematically as a differential equation in molecular biology mathematics. Ordinary differential equations are formulated as expressions of the time evolution of concentration of molecular species in the vast majority of cell and molecular biology models. This equation describes a system with a large number of participating molecules of each type that given that diffusion is high enough for the spatial distribution of molecules to be homogeneous. DNA molecules are modeled using the ordinary differential equation while phospholipid biosynthesis occur at the cellular level using ordinary differential equations. So now what are different types of ODEs we have? Linear, separable and non-separable ODEs. A separable ODE can be written by the following form. And an example provided with its solution is y plus 3x squared times y is equal to dy over dx. So we differentiate it in terms of y and hence we arrive at the solution. So now, what are non-separable ODEs? If an ODE is non-separable, we might need to make it a homogeneous in order to separate it. A homogeneous function is if the nth of every real number is same or equal. For example, x squared plus y squared. And when we expand it with the nth term lambda by multiplying, it has the same power. Hence, it is a non-separable ODE. And we have to make it a homogeneous in order to separate it. So, linear and non-linear or non-homogeneous linear ODEs are two other different types of ODEs. If a function is in the following term, then it's in a linear ODE. An example of a linear ODE is which when Rx equals to 0, for example, the ending after equal sign is equal to 0, then its solution can be as such. While what's a non-homogeneous linear ODE? An ODE is said to be non-homogeneous ODE when Rx isn't equal to 0. For example, if there's 1 placed uh, in place of Rx, it will be a non-homogeneous ODE. Hence, to solve such function, we need to find an integrating factor called fx, which will be used to later multiply the entire equation. And for our last example, we have homogeneous, linear, and reduction of non-linear to linear ODEs. So, homogeneous ODE or homogeneous function is the nth of every real lambda is same or equal. For example, as you can see, x squared plus y squared equals 5x. And then the solution can be made by expanding it with the lambda and we can identify as a second degree homogeneous function. So now, reduction of nonlinear ODE to linear ODEs. A reduction to nonlinear ODE to a linear ODE, we require the need of Bernoulli equation, which would be introduced below. And then a function should be arranged in the following manner to reduce it to a linear ODE. To calculate the a in the above equation, we are able to use the following formula. And after finding the ux, using the above formula, we are supposed to multiply the ux across the entire function and then treat it as a normal linear ODE and solve it using integrating factors and many other theories learned before. So finally, thanks for listening and hope the video was informative. Goodbye.